something available to you to do a poll?
You can just do a poll grouping.
You can? All right, so everybody, I'd like to do this poll. When we get back from break, just inform me, all right? I prefer you to do it, not me, unless there's something really wrong about it. October 23rd, so it's really gonna be the 21st or 23rd. Put the dates up and come back with the date you prefer, okay? Fair enough? I don't know a better way to do this. Okay, now one other thing I'm going to say about the exam, because I'll get all sorts of questions. Is this on the exam? The exam is comprehensive. Everything up to the day before the exam, the class before the exam, is fair game. It's closed book, closed notes. The exam will be like the quizzes. There will be 4 problems that have multiple parts. Do y'all follow me on this? It's not meant to tax you. You don't have enough time. If you know what you're doing, you're going to fly through it and do it very well, probably, and maybe only 2/3 of the time. And if you don't know what you're doing, you're going to be in a world of trouble. And I'm trying to just be fair about this, so you study and you're serious. And I'm trying to encourage you. You cannot cram for this thing. If you're like 2 days before you start studying, you're really going to hurt yourself. My opinion about that, at least. And I've seen that happen. I've seen very good students fail this class over and over again because they cram. Don't do that. I mean, you guys have been here long enough to know how dangerous it is to do that kind of stuff, especially with a comprehensive closed book, closed note exam. But by the same token, I'm looking at his grades. I didn't check the average, but now I'm seeing a lot more very high grades. The average is going up and up and up. So I can only tell you what I'm seeing, and I appreciate the fact that a lot of people are taking it serious. And if you need to see me, please, yes, sir.
Do you like release any practice test resources or anything like that?
There's probably tons of my exams online. I actually don't know. There's a thing called Chegg, I think. I'm not sure if it has all of them. I mean, if you just look up 3810 exams, there's got to be a cajillion of them out there. If you go downstairs, I think it's Eta Kappa News, the Honor Society here. They have all the files. I think for every final and every exam I ever gave, they probably got copies. But I don't know that for a fact. I'm just telling you, I've been told that. Now the real truth is this is the dangerous thing. If you just study old exams and say, oh, that's what he's going to do, you're hurting yourself. The way I make out the exam, I go through the homework and quizzes. And basically those problems are recast and you get them again. That's it. It's not going to be something way outside in left field that you're going to get. It's going to be something you've seen before. If you know it, you'll do it well. If you don't know it, you probably won't do it well. And there's not a lot of wiggle room. I hate to say it that way, but they're very straightforward, they're very simple problems, but you have to know what you're doing. And that's the way all this is. It's not, these aren't wild things like an ME where you have to start with first principles and work out these giant differential equations and come up with a final form and sing it. You're not going to get that kind of crap. It's straightforward. Yes, sir?
Do we get any kind of equation sheet?
No, absolutely. You get nothing. Because these is called very basic formulas and stuff. This is a very basic class. It's like basic physics. There's nothing complicated with it. One other thing I'll tell you too is this. Because everybody asks me in a different way the same question. How can I best study and prepare? I'll tell you this. I would go through the homework. And if just start with the homework I've assigned from the first day of class. If you know how to do it, move through it and do it. If you don't, make sure you do it. Don't just look at the solutions. Work through the problems and convince yourself. Make sure you feel very confident about all aspects of it. From transient problems to, just DC, Thevenin, the Thevenin equation, loop, mesh, nodal. When you get into transient problems, RC, RL circuits, make sure you're confident that you're not kind of okay with it. That's where people get into trouble. I'm trying to just level with you. That's how I do it. And I'd start now to make sure about it. Okay? Yes?
What material, like next week, we got the test as well?
Day before so if the test was not the coming Monday, but the following Monday, Friday's lecture wouldn't be on it. Wednesday's would. All right, let me see, that's the way it looks. The day before the exam, I kind of do a review and I answer direct questions about any kind of problems, all right? Now, I have one other thing happening to me. I have a doctor's appointment today and they can't move it, so I'm gonna have to leave about 15 minutes early, all right? I'm just leveling with you, I'm trying to be fair about this. I'll make it up to you some way. If I have to, I'll do a Zoom lecture online for 30 minutes, but I can't get out of this one, and it's a long story. It's one of those things I have to check that box. Now, for the problems, I want to ask you, since we don't have a lot of people here, have you looked at these problems with RMS voltage? A good question to have is, how many have? Let's try that. All right, usually the serious students do them, or at least try to do them. The real thing about this is I am not going to ask you anything with a wild mathematical function to do an integration. I'm not going to. It'd be very simple. The concept is what I look for and making sure you understand it. I will say this, we're going to do one problem and then I'm going to talk about the most important aspect of RMS voltage and currents are for steady state sine or cosine waves. You have to know how to take the peak value and turn it into the equivalent RMS value. We're going to be talking about this. Does anybody have a problem they want me to do before I just select one on RMS voltage? This can be the general type on that. Anybody? Well, we're just going to do at least one. And these are something that deal only with periodic signals. All right. Did I assign 739? I don't think I did it. Anybody? No? I don't know. I'm asking. Well, I might as well show you how to do it.
Yeah, 739.
Yeah, we're going to do something. I'm going to introduce a new idea too, using this problem. This is problem 739. It just shows a waveform like this and asks something about power that I didn't cover yet. Oh gosh. So this guy would find some way to not put it, it's supposed to be 3. Okay, never mind. This is 3, 4, and 5. So what he's saying is, this is an important problem to at least get an appreciation for what we're talking about. This is going to be the current I of t that's flowing through a resistor. So what he's saying is we have a current here, and I'm calling it I of t, and it's flowing into a resistor. The resistor's value is equal to 4 ohms. And what he wants is the average power dissipated by this resistor. So he's looking for the average power, P av here. Now here's something we haven't covered, but I'm going to do this in I'm going to do it in 2 parts. First, what I want to do is calculate the RMS value of the current. This is key. If you've got that, you've got the power. You're going to see it. You all right? Everybody with me on this class? So if I have that waveform, I'm going to erase this. And that's the current, and I want the RMS value of that current, I root mean square, it's equal to the square root of 1 over t times the integral of I of t squared dt from 0 to t. First, does everybody understand that's just the formula by definition of RMS value of any mathematical function? Everybody got that? Some people mentioned it was part of an equation, but they saw this related to turbulence, effective turbulence, I guess power, something like that. But there's a lot of different ways this is applied in engineering, this particular concept, it's root mean square. So when we do this, you have to understand something. First is, what is the period, if you look at that? The horizontal axis is seconds, by the way. Can you all see it's 5 seconds? That's the time over which it repeats itself. How many see that? Gotta make sure you do. Can you all see it back there or not? Far back? Okay, so 5 seconds. Next, you take a look at this, and you'll notice that I of t from here to here has a different mathematical form than I of t from here to here. Can everybody follow me on that, class? So what I'm going to do is break that equation into 2 equations, and then combine the answer. And as a matter of fact, what I'm going to do is erase this for now. I'll recreate it when I need it. I'm actually after IRMS. So when I take a look at this, IRMS for that waveform would be the square root of, and now it's going to be an integral. First I can take 1 over t here, and since it's 5, I'll just put 1 over 5. And then I have to take an integral. Now from here to here, from 0 to 3, it's a very obvious equation. You take a look at this, what would be an equation for I of t right here in that region, class? Well, it's got a 0 offset, right? At 0, there is no value. Do you agree with that, class? So then, it's really the slope of the line times t. Do you agree with that? I mean, it's rise over run. So the slope would be 4/3, right? Rise is 4, the run is t. And that would be true for t greater than or equal to 0, less than or equal to 3. I hope you all follow me on that. That would be what this portion of the graph could be represented as mathematically. Is everybody good with that, class? How many seats? I've got to make sure you can read my writing back there. Now what about this one? Well, this is a constant, right? This is just -4. So when I do this, I'm going to apply this formula, but I'm breaking it up from 0 to 3 and then from 3 to 5. So from 0 to 3, I have to take I and I have to square it. So I get 4/3 squared t squared dt plus, now I took the 1/5 out in front of this with the bracket, plus an integral from 3 to 5 of -4 squared, or 16 dt. Does everybody follow me on this one? Far back? You guys good? Okay. So this becomes what? IRMS becomes, and it would be the, I'm gonna probably need somebody's help here, but 1/5 times, then I got 4/3 squared, and then I got t squared dt integrated, which is t cubed over 3, evaluated from 0 to 3. So it's really going to be 3 cubed over 3. Does everybody follow me on that integration, class? If you do, let me know, just so I can see your hands. Can you read it? Okay. And it's plus the last one, which is plus. And then I have 16 dt, which is 16t evaluated from 3 to 5. It's going to be 16 times 2, if you look at that. And then I need to take the square root of the whole thing now. Oh, you can mess with this if you want, but so I got the square root of 1/5, and then what do I have? So I really have 4/3 squared plus, might as well just call it 32. I have to multiply that by 1/5. Can anybody give me that value? I think we're gonna get, y'all see what I'm doing, right? It's simple math, just, be careful. What do you get for the answer?
5.93.
That would be amps. Do y'all follow me? But it would be amps RMS. Everybody follow me, class? Now, if you have the RMS value of current, this is the beautiful thing about it. First, if I wanted the power, average power, dissipated with that waveform over a period, since power itself, P of T, is equal to I squared of T times R. Does everybody agree with that? That I squared R is the power at any point in time? If you integrated that and got the average value, so if you took 1/T, the integral, and it would be from 0 to T of I squared of T times R dt. This, in fact, would be Pn. However, I'm not going to prove it right here. This is exactly equivalent to, if you even look at this, you'll see it is. If you take this value right here, what we did, that IRMS is the square root of this right here. I mean, forget the R, of that right there. Do y'all see that? That is the definition of IRMS right here. So what I'm really going to say is P average, if you have the RMS value of current, the average power is just IRMS squared times R. If you're running it through a resistor, does everybody follow me? That would be the average power dissipated per cycle, or really the average power associated with the resistor, or it could be VRMS squared over R. Now, do you remember for DC, voltages or current, power was voltage times current, you remember that part? Or it was I squared times R, or V squared over R. How many remember those things back when we did just resistors and power, right? This VRMS likens the value of the current. It gets an RMS value of current that is in all respects the same as if it was a DC current or a DC voltage. Do y'all follow me? So it's a very useful thing to know, and it also allows you to instantly get the power without a lot of manipulation, square roots and all this crap. If I know the RMS value of current, I can just take that and square it times the resistance, and I have the average power dissipated in that resistor. Or take the voltage and square it and divide it by R. There's not 1/2 or any of that stuff. Y'all with me, class? That's the beautiful part about this, or why it's useful to you. Now, where we're going with this, and I have some notes here. It's something where we're actually going to talk about using the RMS value for voltage and current to get the power like we did the peak value, only without the square root of 2. The best way for you to appreciate this and see it is for me to do it. And then you work a problem or two. By the way, does anybody here live in Florida? I mean, in the area of Florida that's about to be dead. I wish you the very best. I have my family's down in Kissimmee, my mom's side, and I think most of them have left that area. You know, give me a direct hit, but some other people I know that are on the coast, one of them's right in the strike zone. They have left, but that highway coming out, going up through Atlanta, that is absolutely jam-packed. I mean, it is unreal. They're running, I think in a lot of that area, both sides of the highway one way. There's no way to get down there on major roads. So if you're planning to help your parents, I don't know, or your family, I don't know how you're gonna reroute that there. And they closed, I think they closed the Orlando airport, unless I'm wrong. Don't we have shelters here for people? Or not? See, I remember Katrina, you're probably too young to remember, but I remember we had tons of people from the New Orleans area staying here. And some of them became permanent. This is a very large storm system, and a huge number of people, I don't even know the total number, it's 20 or 30 or 40 million people have evacuated, and they gotta find somewhere to go. So, this is as good a place as any if you can get it. Anyway, here's what we're gonna talk about now. It's gonna be the actual RMS. We're using this in a way that's useful, not just an idea. So, you remember before when I said if you had any element, and this, I want to tell you, we're going to be talking about steady state, or constant frequency sources. If we had an impedance Z here, and we assume, you know, all the forms of voltage and current will have an actual value of like some magnitude. I'll just put Vm cosine of omega t plus a phase angle, or Im cosine, and I'll call this theta V, omega t plus a phase angle theta I. And we know we represent these as phasors. Vm indicates the magnitude of the peak value at some angle theta V. Here, Im would be equal to the peak magnitude of the current at some angle theta I. Now that M would be the magnitude of the peak value. This would be equated to simply, better do it right here, VRMS for any kind of a waveform that is cosinusoidal is equal to the peak value, I'm calling it the magnitude, divided by the square root of 2. Now that's real important. So what I can say is if I know the peak value and it's a cosinusoidally varying waveform, either current or voltage, I know the RMS value. You all with me, class? All right, so next, if you thought about this little problem, if I had a current coming here before, where I have a current Im, and I have it flowing in, so it's going to be Im at some angle theta I, and it develops a voltage. Notice the plus is where the current's entering this, a voltage Vm at some theta V. I'm trying to be clear about this. You got this? The power, average power associated with this particular element, I'll put it right here, P av, and it's really the power dissipated, would be 1/2, and here it would be Vm Im times the cosine of theta V minus theta I. How many remember that? Or it should ring bells. You may not remember exactly, but that's the formula. So the cosine of the difference in the angles, something that's very important. And if it's an inductor or capacitor, it will be a 90-degree difference, which means no average power is absorbed by either of those two elements. Now this is in the peak value. With RMS value, this is important, I'm going to put it right here. When you have RMS values, you get this. You get the average power equal to VRMS times IRMS. Remember, VRMS or Vm is actually equal to the square root of 2 times VRMS. That would be Vm here, and Im would be square root of 2 times IRMS. Square root of 2 times square root of 2 is just 2. 2 by 2 is 1. So you get VRMS IRMS times the cosine of theta V minus theta I. And here's the next thing. So now we've got rid of that 1/2 if we deal with RMS quantities for voltage and current. The wall voltage that you have labeled there, 120, it's actually about 117, is the RMS value of the wall voltage. What we do is we label this the power factor. We say the power factor, or PF, is equal to the cosine of theta V minus theta I. For now, just accept it. You'll see why. We would like, and your power company would like to have your house have a power factor of 1 with respect to the voltage and current. It doesn't, but they would like that. Industries are forced to get close to 1. In other words, the voltage and current will have the same, will have a power factor of about 1 because it minimizes the cost that they have of delivering power, because it means the line voltage will actually be lower. And I'll explain this more in a second, but you have to get an appreciation for why we're talking about a power factor, because it's important to the power companies. That's the real reason. And the cost of delivery of power. So this average power is given as VRMS times IRMS times the power factor. You're gonna have to just believe me for now. All right? And something about this that should, at least some of you probably saw, well, this is a little troubling, because you know the cosine function is an even function. By that I mean cosine of x is the same thing as cosine of minus x. Do you all follow me on that? How many understand that concept? What it means is, you don't know if theta v minus theta I is positive or negative, because the same cosine value would be associated with either. So they talk about something called leading and lagging power factor that I'll get to in a second. It has to do with if the current angle is greater than the voltage angle and such not. But I've got to show you this applied so you have an appreciation for why it's important. So with this, the best thing to do at this point, in the time I have, this is on page 217 of your textbook. I'm trying to give you the exact location of it. And I'm not going to quit, because some people are thinking, are you going to give us a question on an exam or quiz where you ask us to do finding RMS values for some crazy mathematical function? No, I'm not going to. But you have to know what it is for peak values related to RMS values for sinusoidal varying waveforms. So let me show you an application of this. And this is on page 218. And hopefully, this will make it a little more, matter of fact, I think we're doing it right. So what he says is there's a power company here. And he just has it as a blob. And then the power company has some kind of a line that has 0.1 ohms of resistance. And then they say they have a load. Now this is the important part. So they're saying that there's a load or something that is actually getting their power. And the load has an average power, write this down too, an average power of 100 kW. Whenever you see a W, a kW or anything like that, watts is average power. Y'all follow me? You're going to see that there's different types of power, which will trouble you at first if we get over it. And here they say that you have a power factor of 0.66, but then they say lagging, and I'll get to what that is in 1 second. And they say one other thing. they're gonna say that the voltage across this load is 480 volts RMS. Can y'all follow me in the back, by the way? That's 480 volts across this. The average power dissipated is 100 kW. And they say that the power factor is 0.66 lagging. Okay? So, now I've got to make sense of what I just told you. And what they really want to know is how much power is supplied by the power company. So the question is, what is the total power supplied by this power company? We know we're using 100 kW there. Do y'all follow me, class? So we're going to do it by getting the current right here. Y'all agree that the current here, that's called a line current, IL, it's just the current flowing from the power company in a line to the actual load. You can think of this as an industrial load, like at a mill or something. When you do this, you start with a basic equation for power. We know average power is equal to VRMS times IRMS, right? Times the power factor. Does everybody agree with that? I know you're just exposed to it today, but we have the voltage RMS across that load. We have the power factor. And we have the amount of power dissipated, and we need the current, IRMS. So I can see that IRMS in magnitude would be equal to the average power divided by VRMS times the power factor. So it's 100 kW, or 10 to the 5th, divided by 480, and then divided by 0.66. I'm hoping he tells me what that is. But you can tell me. I can't find it. So it looks like you get 226.45 amps RMS. 226.45, I think that is right. Can you all follow me in this class? Now, what does that actually mean as far as the power supply? Well, there's 100 kW there, but there's going to be power dissipated by this resistor. And the power dissipated by that resistor would be equal to IRMS squared times the resistance value. So that's equal to 226.45 squared times the resistance, which is 0.1, and you must get that somewhere. That's 5.13 kilowatts, I believe. You could put 5.13 times 10 to the third watts, but K just means 10 to the third, or 1,000. So that means the total power supplied by the power company right here would be 105.13 kW, or about 5 kW more than is actually burned. Y'all follow me, class? Now, if that power factor went to 1, it would be even less. That's the idea behind this. But before we go there, I have to tell you what this lagging means. All right? So when you have voltage and current, you're always going to have something where the two are out of phase, but one is considered lagging and the other leading. Now, I have to be clear about this. So whenever you take a look at the actual voltage and current, if you have a voltage waveform, and I'm just drawing this as a line here, if you're going to have some voltage RMS and at some angle theta V. Can you all follow me on this? Now, without getting into all the math, this thing, as time goes by, is actually revolving this way. You're gonna have to just forgive me. If you take the projection of this onto this thing right here, this right here, this, if you did this, this actually would be VRMS times the cosine of omega t plus theta v. And as time increases, this rotates counterclockwise. Can you all at least go with that? And the real power is going to be the projection on this axis. Can you all follow me? I'm sorry, the real voltage is the projection on this axis, not power. Sorry. You all with me, class? Now, there's also going to be a current. And the current's going to be down, I'm on purpose putting it down here. It's going to have a value of IRMS. And it's also going to have an angle. So it's going to be IRMS at the same angle theta I. Now, they are revolving counterclockwise. Just try to appreciate this. I'm trying to make it as easy as possible. If the voltage waveform is mathematically in front of this waveform by less than 180 degrees, in other words, somewhere between here and here, all right, the current is considered lagging. Does that make sense to everybody? It's behind. It would like to be there, but it's not. This would be a lagging, and I'll give you an example. Lagging current. And that means a lagging power factor. Now, if the opposite was true, if the current was ahead of this, y'all follow me? In other words, if the angle of the current, say this angle was 45 degrees, but the angle of the current was 60 degrees, in other words, it would be higher up, then it would be leading. And how many have ever heard of the statement? I'm going to ask this. If somebody does, I'll be happy, but I'll be surprised. Eli the Iceman. Anybody here know that saying? Anybody at all? I took you do. Did you have electronics in high school or something?
It was physics too.
Yeah. Well, I had electronics in high school. It's a standard thing. Any electrician will know this. Eli, well, L, inductor. You know that symbol? I'll put it up here. It's the last thing. I got to get out of here. It's going to be late. It's Eli the Iceman. E is the British symbol for voltage. I is current. When you have an inductor, voltage leads current. That's all it means. L is an inductor by 90 degrees. If you have a capacitor, current leads voltage by 90 degrees. Y'all with me, class? So whenever they say a power factor is lagging, they would say it is inductive, or the predominant reactive effect is inductance. When they say it's inductive, just listen to me and I'll be done with this. If you look at this voltage right here, they give you 480 volts. I'm assuming the phase angle is 0 degrees. So they say 480 volts at 0 degrees, and that's RMS. That means the current we calculated, IRMS here, which is, what was it, 226.45, will be at an angle. Now listen, if you take the inverse cosine of 0.66, can anybody do that for me? Inverse cosine probably has it in a book, but I don't really care. I want to just get it from you.
What is degrees or radians?
Degrees. You got it for me?
48.7.
48? Call it 48 degrees. It means this current right here, this is the voltage, it means this current, because it says lagging, will be at minus 48 degrees. Or it will be behind the voltage waveform by an angle of 48 degrees. Do y'all see this? That is the only thing you need to know. If it was leading, it would be plus 48. I can't get into this anymore because I'm really probably going to be late. I'll probably get yelled at. So be it. Anyway, I'm going to give you some homework about this. Please, if you're having trouble, catch up on the areas you don't understand. And then give me the results of that when we get back on Monday for break, right?